All right, so running the show yourself. So, but this is good. Thank you so much for coming. Sorry that you're late. You're technically 4 minutes late. Machine learning, you have to do things fast, so I'll catch up. My name is Sam Bassett. I'm a professor of statistics at this wonderful institution, in the College of Natural Sciences and Mathematics. I'm also in charge of a center called Center for Computational Applied Mathematics, CCAM. We do a lot of these workshops. We have multiple workshops on software representation, on programming, on data analysis, on modeling, and also in sciences. Some of our esteemed science colleagues are here and they present their work. Anything that has to do with computation concerns us, and we're very pleased to introduce to you today's talk, which is given by myself and my colleague Valerie Pointer about statistics in the age of big data. Why is this? Why is it that statistics or machine learning play some important role in sciences and in industry? And how do you start that journey? Basically, that's the idea. So, in what comes, I start by just introducing you to some terminology. Most of you have seen or are familiar with these concepts. I'll be quick. But for those of you who are new to these ideas, I'll just go over them, give you a broad overview of the story, and then I'll delve into technicalities. Valerie's going to take over after I go through this introductory part of the story, and then I'll close with telling you what neural networks are and how we utilize them in the context of scientific inquiry. So, largely speaking, the terms that are very popular these days, I had a couple of students stopping by in my office right before this talk, and they were telling me that all they hear at work is machine learning, big data, data science, neural networks, deep learning. What are these things, and why have they become so important? That's really the gist of this presentation. First of all, data mining. You might have heard this term, data mining. If you have taken a course in statistics, we advise people that if you encounter a big population of data, go about taking a sample from that population, analyze that sample, and then try to make statistical inferences or mathematical modeling based on the random sample that you've gathered and generalize it to the population. Data mining concerns just digging into the big population of data directly without sampling and trying to find patterns in a sea of data, in a cloud of data. By pattern, I mean anything that is not usual, upward trends, backward trends, outliers, data that look seemingly off track with everything else. Data mining is a sort of set of technologies or tools that would allow you to study a population of numerical information in its sort of panoramic view. There are two types of data mining techniques. One is called descriptive, which is basically just exploring a set of population of data or numerical information, just mining through data and look for patterns. The other one that concerns us in this talk is called predictive data mining, where you have lots and lots of data, and then you try to employ techniques associated with statistics and stochastic modeling to figure out what you can tell in terms of future observations. Prediction. Prediction is presumably one of the strongest tools in the artillery of a mathematician or a statistician or a computer scientist of this age and time. They are able to look at patterns in the past and tell a story about the future, potentially, with some level of uncertainty, not 100% sure. If you follow the elections, you know that there's always somebody predicting something. They failed horrendously in the last presidential election. So data mining has to do with finding out what is it that you want to study, what's the target population, and then a lot of data cleaning. Oftentimes, real-life projects are not textbook data, where everything is beautifully processed, comes in a matrix, you just read it in some fancy software, you click a button, and then gives you some t-test or regression or some funky model. Real life is far more complex. Data comes in awkward patterns and forms, and a good chunk of time is spent on just processing it, making it, or pushing it to a level that is apprehensible, understandable by the analyst. And that data massaging, basically data cleaning and data pre-processing, oftentimes is the biggest and the most challenging part of a scientist who deals with the analysis of data. This is something that we rarely teach in our courses, but we began to sort of think about. All of us, at least math people, stats people in this room, we know a whole bunch of methods and techniques of how to model data, but we rarely talk about how this data were collected. Where did it come from? What is the source of it? Was it randomized or not? Is it reliable or not? That's the most sometimes important part of the story. And it takes a while before you get to manipulate the data to a point that you can actually run a model over it. Then there's data visualization. Valerie's going to talk about that. All sorts of interesting techniques that will make understanding of the relationship between the variables in a data set more meaningful. We have a data visualization club in this college, in case you guys didn't know about. You raise your hand, Randy. That's Randy, one of our graduate students. They have a club. All they do is data visualization. They look for cool methods and techniques and software and platforms with which you can actually visualize big data. Talk to this guy. So, if you're interested in data mining per se, namely a big, sort of an approach in which a big deal is pre-processing and massaging data, this is the textbook you might want to consult with. One of the best, I've seen many titles on data mining. This is what I do, but this book is really comprehensive, and this lecture is really sort of on the workshop-based educational sort of services. So if you're interested, look into this textbook. Then you hear the term machine learning. Everybody's talking about machine learning. It sounds really cool, and it's really, really cool, but it's not that sophisticated. And I'm not sure if it needs an independent definition onto itself. Basically, machine learning is a set of techniques that allows you to develop methods that are smart enough that can learn from patterns of data and bring about that knowledge that is accumulated throughout time in order to help you to make decisions under variation or uncertainty. Remember, the whole language of statistics or applied mathematics these days is the stochastic language. by which I mean randomness. There's a good deal of randomness in everything that we observe. We never dig into the core of data. Can somebody get the door for that lady who wants to go? Hold on. Sorry. We never get to the core of data. We never collect all the data that there is. It's impossible, right? Any field that you're at, whether you're doing it in your laboratory or observing what happens in the nature, you can never collect the entire set of data. As such, probabilistic thought process or point of view about modeling says, I'm going to associate some level of uncertainty to what I'm observing. Okay? And that's the core of decision making. How can I optimize my decision making under uncertainty? So when you hear machine learning, you're thinking algorithmic procedures. You're thinking translating mathematics or statistical modeling into series of approaches that can be repeated and result in an output that helps you understand the phenomenon that you're studying. That's really the core of machine learning. As such, the idea of learning from data, and I will talk about that in a minute, the idea of learning from data is inherent in the definition of this type of modeling. It's iterative, that it constantly learns, becomes more and more accurate, and generates outputs that cannot be corrected under that system anymore. It gives you an ultimate accuracy based upon what it's sort of built upon, or its infrastructure. One of the simplest, very easy to code applications of machine learning is when you write on your smart iPads, right? When you write an 8, for example, and machine understands that you were talking about 8. You are not writing an S or a B or some other funky icon. You meant digit number 8. How does machine do that? People write in all sorts of forms and shapes. Not everybody has fancy handwriting. Why would a machine appreciate that you meant an 8 in the context of a text or an expression of an idea? That's done through what we call pattern recognition. Basically, you juxtapose a grid on that handwritten piece of work, and you pixelize it, translate it into little tiny cells, and through what we call neural networks, and we'll talk about that, we translate that image, that shape, onto a pattern, which is a discretized output of a statistical modeling. We call this classification, categorization. It's the gist of machine learning, basically, classification. We predict with some high level of accuracy that what you meant was an 8 and not an S or a B or some other letter or word. Okay, so 2 things to get it right before we become more technical. The first thing that is really important is to appreciate that the big sort of purpose in machine learning is prediction. There are 2 types of modeling in applied math and statistics. One is what people have called traditionally as regression. Many of you who have done some statistics have heard the term regression. There is some output, some response variable, and a whole chunk of predictors. And you're putting values into that sort of predictors by building a model and trying to see what comes out of it. That's called prediction. Model-based scientific guess about an unknown or newly observed data point. It's called prediction. But then there's classification. You give me a bunch of data, and you want to know where these data go. To what class should I allocate them? That turns out to be really, really important. I would say 95% of all of machine learning, modern machine learning, is about classification in some fashion. So really, if you want the big, high-level algorithm of all of machine learning techniques, that would be it, in my view. you have data, and as you collect more and more data, you accumulate knowledge. You combine these two sources of information, new data, knowledge, and you wrap them around what we call modeling. Some sort of a mathematical expression that allows you to get closer and closer to that output, to that classification. And you repeat this process up until the point that you feel that there is no more contribution to accuracy of your output. Whether you decide that or the machine decides that, you know, I can't make it any better. I really think that what you meant was an 8. For that reason, the machine makes mistakes. There's no way that you type, if you have a clever software that tries to translate your handwriting mumbo jumbo into a meaningful text, there's no way that it comes with 100% accuracy, but we become better and better because our elaborate models become more and more elaborate. Because I'll show you in a minute that from neural networks, we're moving towards deep learning. We're just making this whole story more articulate. So why a statistician is talking about what seemingly computer scientists do? Because the moment we start talking about modeling, you're in the world of statistics, applied model, mathematics. You're in the world of building models that allow for that randomness. In our world, nothing is deterministic. I am willing to make meaningful predictions, but not 100%, with 100% accuracy or the confidence, they call it. It's a dubious word, but just to be exact, I'm in the world of making decisions with some level of uncertainty. That modeling side is where my expertise kick in. Almost every big-time concept that you see in modern machine learning, if you go to computer science, hopefully we have colleagues from computer science here, the gist of it is statistical. What they have been able to do in the last 15, 20 years or so is because they know how to tackle the problem of hardware and software, they've made it very, very universal. And so who is the person who can do a decent job in machine learning these days? It's a person whose expertise consists of mathematics knowledge to some level, statistics knowledge, and computer science. Some people like to call this statistical learning. That's the more radical ones amongst us. Bayesianism is a way of thinking about all of statistics. You hear a lot of terms, all of you are familiar with more than I do, or more than I am, with things like hypothesis test, confidence interval, classification. You've heard these things. You've taken a course in stats, you've taught a course in stats, you know statistics. Bayesian is just a point of view that you are more than welcome to adopt when you think you can benefit from two sources of knowledge or information. Bayesian is a statistician, is a scientist, is a scholar who takes upon herself to connect two types of distribution. One is what we record through that likelihood function. That's all of statistics. If you ask a person who's walking by on campus, what is statistics? They will tell you, oh, it's the science of analyzing data. Fitting models to data. That's likelihood. That's classical statistics. Likelihood is a term that R.A. Fisher kind of devised. R.A. Fisher, students in my class know I talk about him all the time. This guy solely kind of sort of created or came up with the idea of modern statistics in a span of 10, 15 years, from 1910-ish all the way to 1925, 26 or so. So this guy developed the idea of likelihood. The chance, the likelihood, the probability of observing an entire data set. We call it the likelihood function. Given that there are some parameters in that function. Parameters are unknowns of the statistics. If I'm studying population of fish in the sea, and I'm interested in how much food they take in grams, then that would be an unknown. You'll never be able to reach out to every possible fish who's swimming there, right? It's impossible. That theta guy is unknown to me. I call it a parameter. So given that there is such a thing as an unknown parameter, let's try to come up with some probabilistic language of modeling it. Bayesian is a guy who, or a girl, who looks at a data distribution and the prior knowledge about what we are going to study. Bayesian is a person who looks at the paradigm of scientific discovery, which is constantly a combination of expertise and data analysis. Every single one of our colleagues in sciences, you talk to them, for them to publish, they have to do some data analysis at some level because they collect data in their labs. Their research is extraordinarily sophisticated. Don't get me wrong. There's no way I can understand what a chemist does at that level, or a biologist. Very, 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 very technical. But what I do know about their work is that at the end of the day, they collect data. Bayesian says, let me connect these two pieces of information, their expertise and the data that they collected. And all of statistical inference is done through the function on the left-hand side, which we call a posterior distribution. Prior plus data is posterior, or times data. I don't know if you're a football soccer fan. A couple of years ago, they signed up David Beckham. Have you heard his name? They paid like load of money to get this guy. Huge, $250 million. That's like 1 year's salary of a professor at Cal State Fullerton. They hired this dude, and he was incredible. He's famous for his free kicks. There's a bend to it. If you watch the UK games of the World Cup and so on. Anyways, he came here, and then the moment these big guys show up, some statistician is going, okay, so who cares? But they do that. Okay, they do that. So he only played 2 games and scored 1 game, and his likelihood function is that red curve. We modeled it by Poisson distribution, some funky distribution. Then, however, the prior was all the games that he had played before he came to LA Galaxy. He was playing for Real Madrid, a big-time club in Spain. So we had a lot of knowledge about what he's capable of, and what he knows, and what he can do last minute to change the tide of the game. That blue curve, which is the prior knowledge, is very sharp peaked. It's very concentrated. There's a lot of concentrated knowledge about David Beckham because when he came here, they come to US when they are about to retire. It's LA, surfing, all that stuff. So they come here after they did they hired actually David Beckham because, not because of his game, but his name, right? All the merchandise and all that. So posterior is the green curve. Look how it stands between data and prior. This is how a Bayesian makes inferences, sort of mediation of these 2 sources of knowledge. Of course, this is a cheesy example, but in real science example, actually this ends up being extraordinarily helpful in making sense of scientific data. Neural networks. You hear this term all the time. There's nothing mysterious about it. First of all, it really started from neurons. Neurons, biologists in the room, apologize. I don't know much, even though I've done a lot of research on neuroscience, but I don't know much. Basically, brain cells are typically called neurons. We collect we have tons of neurons in our cells. And neurons, somebody says, I read somewhere that it's actually an active area of research, how many neuronal cells are out there. Somebody estimated recently 100 billion cells. They more or less look like this is the simplest kind of neuron that you can come across with. It has, look from left to right, soma, the body of the cell, basically opening gates where some chemicals come in, and then the body of the cell where electrophysiological stuff happens. And if the magnitude of that chemical processing is strong enough, it translates into spikes, into action potentials, and then through these action gates, output gates open, and then transmit the knowledge, the signal to the neighboring cell. That's signal processing 101 in the brain. So many years ago, there was a scientist, two scientists, two mathematicians. This is World War II, 1943, McCulloch and Pitts. It's a fascinating paper for those of you who are interested in the history of these stuff. They actually looked at the body of the cell and they said, I can run a model, devise a model that tries to mimic this neuronal cell. Look how, it's basically trying to understand what this input channels are, what the body is, what happens in terms of manipulating data or information, and that output tries to reflect upon the fact that if there is signal processing and it's successful, information will go out to the neighboring neurons, to the network of neurons, neuronal nets. Then they came up with this simple model. You have a bunch of inputs. There is a processor. In this case, processor is just adding ones and zeros. Very simple. This is early 90s. There's no computer power the way there is now. And basically, you define a threshold. Let's say if 10 neurons are coming in and my threshold is 6, and if I got lucky and I got more than 6 ones, I went beyond the threshold, so the output gate opens. That was their model, the famous McCulloch and Pitts model of 1943. It took mathematicians many years, till 1958-62, two seminal papers by Rosenblatt, where they actually looked at this and tried to make it more articulate. They said that information do not come in uniformly, but they come in with different weights. The beauty of Rosenblatt's model is that he came up with those W's that says that the pieces of information that you receive are not equally important in processing data. So he came up with this weighted translation of neuronal processing, signal processing. His paper is incredibly beautiful because it sort of encompasses what we know about modeling that gets into stuff such as learning. If you read that, I was a student in computational neuroscience, so one of the first things that I had to read was Rosenblatt's 1958 paper. He says there are 3 things that one needs to figure out in order for one to understand how information is processed or are processed in the brain. 1, how do we receive information? 2, how we store them. 3, how we utilize them in order to make decisions. That's like 1, input, 2, analysis, 3, output. And I copy-pasted from his paper. This is his paper. He came up with what we call now a more elaborate neuronal network with a hidden layer. He just drew it. He didn't have a computer, fancy Microsoft. How do you do this? Microsoft PowerPoint or something. Okay, so this is really the model for modern neuroscience, neural networks. Data come in, we analyze them through these hidden layers, which is basically a weighted averaging or weighted processing of those input cells. Rosenblatt called them perceptrons. And then we analyze them through sending them out via some nonlinear function. We call them activation functions, typically a logistic function, sigmoidal function, for those of you who are into the mathematics of it. And the reality, however, is that if you have 100 billion neurons communicating with each other, building this network, understanding this network, turned into a massively complex, nearly impossible task. Just for the teachers in the room, this idea of Rosenblatt has not faded away. This has continued to this very day. And there's an area in neuroscience, which is neuroscience of learning. How do we learn things? There's a seminal paper by a group in Princeton that actually shows that selective learning, paying attention to what you learn, can be a very strong brain modulator. This is important because for some of us, this has had sort of significant effect in our teaching. People learn at different paces, and that's a scientific outcome of having different dynamics in neuronal nets. As such, you cannot necessarily make a calling that this is a better student or worse student because they answered the question faster. It's brilliant that they do, but some of us need more time to process information and to utilize them. Like most of you, it took me years to really deeply understand some of the most profound ideas in mathematics and statistics. I could perform them as an undergrad or even a master's student or PhD student. I could get good grades, but I had no idea what I was doing, to be honest with you. So this is a simple neuronal net. The more you add these hidden layers, the more elaborate the networking becomes, then you're going to have more and more transformations and weights to worry about. Computationally, the task will translate into coming up with some sort of way of bookkeeping of these activation functions that are being applied to these set of weights or processors. To be honest with you, this is a really simple scenario. A real task of image processing, a good image processing task that is done with deep learning would require pictures that come in pixels of typically, 32, all the way to 563 by 563. That's just one of those green ones. And then developing these layers, and then suddenly you're in the world of billions of connections. Computationally, how do you make this possible? Deep learning allows you for some of the weights to be shared amongst these and some creative ideas like convolution and pooling and stuff like that. One day I will give a talk about deep learning. I don't want to waste your time with it. Just be aware that there are ways that you can make these techniques computationally more feasible. The gentleman in the back wanted to ask.
Yeah, is it necessary to add multiple hidden layers, or can you just use one layer and add more neurons?
That's a really good question. Do I really need more hidden layers? Maybe I can just do the job with one layer. The answer is sometimes you benefit from that by becoming more accurate in your prediction. For example, in image processing, if the first layer so you have a bunch of, take a picture of students in this class, that if you allow for the first set of your weights to translate via some nonlinear function, typically a sine or a sigmoidal function, to translate only the shades or sharp edges or the hues. And then in the second step, second hidden layers, you allow for retrieving, let's say, color. And then the third one, the very sort of crystallization or sharpness of the picture. And on the fourth layer, then you allow for more weights to be concentrated simply on characteristics of image processing. As such, even though you pay the price of the process being far more expensive computationally, but the outcome will look much better. It's like the world of TV moving from a good old-fashioned HD to 4K HD. It is really nothing but faster image processing. What is data science? I mean, it's mostly, it's just like the same things, stats, machine learning, but somebody decided that data science is cool. So since you guys took this course, we're sitting here, in your resumes, you're allowed to say you're a data scientist. Analytics, what is analytics? What we do, building models, okay? That's analytics. Again, it's fancy. How much analytics do you know? Namely, how much computer science and statistics or applied math you're familiar with. So, yeah, you qualify. Before I close, old-fashioned statistics is cool, but most of the times in this day and age, they are incapable of telling the entire story. Everybody in this room, as long as you haven't taken a course in basic stats, knows what the t-test is, right? T-test tries to see the population of, let's say, one group or two groups, how close they are to each other. This is a famous example by two masters of statistics, Efron and Trevor Hasty. They said they were looking at gene expression data. So y-axis is some sort of measurement of gene expression. And they had 72 patients. And they measured only one gene. They tagged it as gene number 136. Okay? And they looked at 72 patients. Some of them were in, 47 of them were in the top group. This is two types of leukemia. And they calculated the t-test. T-test came back, t-observed, came back as 3.01. Technically, if you go to a t-test table or have your machine calculate that, this p-value is going to be very small. You can immediately conclude that one shall reject the null, and remember reject the null, this one. So reject. But the reality is that they didn't have data for one gene. They had data for 7,000 genes. And then they saw, when they did the same thing in terms of two types of disease for 7,000 genes, and they looked at one type of leukemia versus the other one, when they sort of expanded or broadened the zoomed out, they realized that 3.071 is no longer that radically outlier number. In other words, there were about 5.2% more genes that did even worse than their measurement. If they were about to stop and say, based on statistics, I shall reject the null hypothesis, that would have been some sort of a misguiding statistical analysis. Once they dug into this and looked at more genes, they realized that the story has been reversed. Nobody knows why exactly, but many of us think that this is because of all those assumptions you make. Let's assume that data is normal. Let's assume data comes from this distribution or that distribution. T-test is known to be very sensitive to normality of data. And even if you have tiny little outliers, t-test and all that, the class of these tests go wrong super bad. Yet everybody does t-test because it's easy, it's everywhere. Even, what is this? Excel does it, right? So, why not? Why not? Because things can go wrong. When you go big data, the image changes because some of those assumptions collapse. That's why machine learning can be potentially useful. Since I have more coffee to drink, I let Valerie take over. I'll be back about neural nets.
All right. So the goal kind of my portion of the talk is I'm just going to present a case study to you guys of a real data set. And I'm going to kind of just use it to show some examples of some of the methods that Dr. Bissetta just went over with you in more of a broad sense. And of course, there's so many that we are not going to get to cover, but this at least gives you a nice little summary taste of what's available. So the data set that I'm going to use is from the UCI repository, and it's freely available, so you can click on the link and get it for yourself. I myself am also not a biologist expert, so some of these words are, there's probably other people in this room who could better explain what some of these definitions are, but I can give you the general gist of what the goal and what these types of data, or what this data set is talking about. So along the lines, keeping along the theme of gene expression, this is exactly what this data set is. And in fact, this data set, though, is quite large. We have, for about 800 subjects, over 20,000 different genes in which the expression, which is some sort of measurement of light. So it's in volts is usually the units that are used. And the idea is, for this data set, they would like to know what gene expressions are associated with a particular tumor type. So these 800 subjects all have some sort of cancer, with and then within their subgroup is a particular tumor type. And we've got, I will refer to these as BRCA, Kirk, Code, Ruod, and Prod. Those are the 5 types that, so each subject can only be one. And we are going to kind of go through and see if we can pull out from this very massive data set which genes are important or associated with these different types of tumor types. So the first step that everybody needs to do when they get a data set is to actually visualize your data. Now, this is not very easy often with big data. And so I think sometimes people tend to skip that part when you've got big data, which is really unfortunate because you should never, ever underestimate the power of the thought. The thought will, and especially as humans, we are so good at naturally seeing patterns or seeing interesting features about the data. So you're really kind of just cheating the data and cheating yourself or the research project if you don't actually just take a look at it yourself and kind of just get a practical assessment of it. Okay, so all of these analyses that we do in this talk is done in R, and ggplot is a library in R that offers some really cool visualizations. Yes?
So what's big data? Is it 10,000 more, 100,000 more?
So
what's considered big data?
Big data is usually data that you have struggle actually fitting typical models to. So 20,000 genes becomes really difficult for us to fit, say, a standard linear regression model. So what you'll see in this first, after we do the visualization, what you'll see is that we're going to have to deal with some sort of dimensionality reduction before we can move on to answer our question. Does that make sense? All right. So ggplot, I Google stuff all the time for ggplot. There's a lot of different things you could do, and it's really nice we live in this world of the interwebs, and there's tons and tons of examples that you can use as templates. It's kind of intimidating at first, but once you kind of get the hang of it, then it really becomes very powerful. Okay, so what I did first, spoiler alert. What I did first was just go ahead and look at 2 subjects, because I want to see what does this data look like. What is the distribution of gene expression look like for this one subject, or I have 2 up here that we observed. So the genes are on the X, and the gene expression is on the Y. And so when I look at this, it's like, okay, it looks cool, but and my subject number 7, he has tumor type Kirk, and then subject 73, he or she has tumor type Ruod. But when I look at this, I don't really know where to go with this. So it looks like a big mess to me. I mean, you got some, and it's like when you look up in the sky. So this is I should say a warning to human ability to detect patterns. But when you look up at the sky and you see clouds, and all of us can come up with some sort of shape. So I mean, if you stare at this long enough, I'm sure you're going to start seeing faces in here. But as far as being able to tell differences, I mean, there's definitely some areas of difference. But then again, this is just for 2 individuals. That's it. So, but the individuals can have their own unique individualistic features. So we need some sort of summary, a way to summarize. And in fact, I went ahead and I just said, okay, let's just pull out 2 genes, and I'm going to look now 1 gene on the X, 1 gene on the Y, and then look at my about 800. I think there was 791 patients that we looked at. I'm like, okay, well, let's look at everybody. Gene by one gene. That's a mess. These 2 genes, obviously not helpful in detecting the tumor type. So the colors represent the different tumor types. Everything's kind of just mixed in, convoluted. So this whole guess check thing isn't going to work for me too well. So what I ended up doing instead is I said, okay, can I take the average of each gene expression? So I have 20,000 something gene expressions, and I just averaged that expression within the 5 tumor groups, the subjects within those 5 tumor groups. And then I say, okay, well, I need to be able to say, is there a way that I can like look at the average difference between types? So I looked at 3 pairwise differences. And again, this is just the difference in the average. And I try to kind of incorporate all 5 groups somewhere in here. And I said, okay, if there's a big difference in the observed average, then that's kind of a sign, at least, that I should be able to detect or pull some of these tumor types out. So I went ahead and I highlighted or bracketed the 2 extremes. We have this point over here and this point over here. So I could identify that in my the matrix of differences. And then I'm going to look and plot at those genes, because before I even go in and do these analyses, I want to make sure that there's genes that kind of look like there is going to be something I could pull out from it. So that's how I ended up deciding this one. So I looked at them differently first. So here's a nice visual that you can also do in ggplot. And so we've got the different, again, the colors represent the different tumor types. And we can see here in gene 3540, we've got Kirk can be very distinguished from the code or coad. And that one was this code versus Kirk. That was this guy right here. So this gene really does seem to help, at least visually, we haven't done analysis yet, it really seems to help distinguish those 2 types of tumors. And then this one really seems to set just the WAD separate from everybody else. And then you can plot these guys together, and now you can kind of see the clusters start emerging a little bit more. So it's okay, there appears to be something here in this data set. Hashtag DC roots. All right, so we can move on. Now it's worth it looking at it a little bit further. So we do have over 20,000 gene expressions. If you put that in any sort of model, then it's not gonna. Most of the models would end up breaking. So, but it probably seems that we could pull out information. Probably not all of those genes are giving super important information, or they're giving similar information. So is there a way that we can reduce the dimensionality in which we can extract a summarizing information from all of these genes? And so that kind of brings us into a foundational concept in statistical and machine learning, in which there's 2 different processes. So you can treat something as a supervised learning problem if you have specific responses, or you can look at it as an unsupervised learning problem where you look without having some sort of response. Now, technically we do have a response, but before we can utilize the response, we need to extract the necessary information from those genes first. So then that leads to more of an unsupervised learning. And PCA, clustering, those are all unsupervised learning. PCA is actually what I'm going to do both of these on this data set. PCA is going to help us to reduce the dimensionality of those 20,000 genes. And then later we'll come back with doing supervised learning, where you would do either regression or classification. For this problem, it's going to be classification. But the process, the idea is kind of the same as in regression. Okay. So for my next diagram, I dedicated this to the Dean of the Natural Science and Mathematics, Dean Johnson. I don't know if she's still here.
She's back.
Oh no! All right, somebody paid this time point in the video so we could show her later. And again, this is a non-technical talk, so the goal is to kind of just try to give some intuition behind these methods. So here is a diagram that kind of tries to explain what principal component analysis does. So here's our subjects. And so what happens is we go ahead and we apply this principal component analysis. What comes out of it are features that try to pull out or explain, maintain the variation. So for example, in this data set, our animals here, a lot of different weights. The range and the variation of the weights is quite large. So if we know the weight, then we could actually probably get pretty close to knowing which animal it is. So that's what I mean by variation is information. So if we could, and the weight would be called our first principal component. So the first principal component tries to find the variable, which is usually unbeknownst to us, in which can explain the biggest amount of variation. And then the second one then tries to explain what's left, the most that it can of what's left. For every subject, basically, or however many subjects you have, that's how many principal components that can pop out. But the thing is, this is where the dimensionality reduction comes into play, is usually we don't need all of them. We can usually cut off after a certain number of principal components. Questions?
Does PCA find those, attributes in the right-hand column for you, or are those things that you provide?
Yeah, so this is just as an example. So we don't know that it will find it for us, but we don't know that it represents weight, for example. We just know that it found this PC1, principal component 1, but we don't know what it represents.
Is that kind of similar to K-means clustering?
So clustering is a little bit different than the principal component analysis. So in clustering, we're actually trying to divide our subjects into similar parts, similar pieces. Here, all of these subjects are going to play a role in every single one of these variables. So, and this is what it ends up, and this is how where the role comes in. So all of the genes are going to play a role in PC1. So this is the beauty of principal component analysis, because we're not getting rid of any genes at this point. We're just transforming the space projecting into a smaller space, all of the information. And then what happens is, okay, we are going to have to lose some sort of information, because we're not going to, if we took all the PCs, we're not really gaining any sort of dimensionality reduction. So we got to figure out where to cut. Where should we make the cut? To do this analysis in R, the function is just the PR comp. Typically, since PCA is sensitive to the units, so gene expression, everybody was on the same units, so I did not need to scale everything down. But typically, you will want to scale if you have data that coming from different unit sources. Okay, so this is just kind of an eyeball plot, kind of giving you an idea of what type of information the principal components actually contain. So the x-axis is the number of dimensions. And so this first plot, lambda, is actually representing the variance within each principal component. So our first principal component, boom, a lot of variation right there. So it contains a lot of the information just in principal component 1. 2 and 3 also. I mean, it really kind of becomes at least relatively small after you get about 7 PCs. And then here you've got a lot of variation in your genes in general. So this gives you the percentage of variation that is explained by your PCs. So here we're looking at about 50%. Now the general rule of thumb is you kind of want to go about 80%. But for the purpose that we have here, we really want to reduce the dimension quite a bit. And I mean, I know it's coming, so I know it works. But we went ahead and we went with 7 principal components. And mostly it was coming from this plot. There was like a definite gap between these two where I say, okay, this seems like a reasonable cutoff. And I'll discuss a little bit later how to actually choose what the appropriate principal component would be. So, but for now, we'll stick with 7. Okay. Okay, so now I wanted to just show you what information is just in these first few principal components. So this one, the PC1 is on the X on both, and then we have PC2, PC3. Just PC1 and PC2, so we've got our color coded because we actually do know which tumor type these data are associated with. We've already got this clustering going on. There's a little bit, there are pieces of overlap. So this is where, probably PC1, PC2 isn't going to do it just on its own. You're going to probably get some errors in classification because there's a lot of overlap here. If we add more dimensions, so PC1, PC3, now there's a little bit clearer cut between this BRCA and this LUAD tumor types. And then adding even more, you can tease apart those groups even further when you take it to a higher dimension. So while we're here with the unsupervised, this is kind of like a little sub story. It's not part of the main story, but I wanted to give you another example of unsupervised learning, and this is clustering. And the diagram that would then represent clustering would be to try, what it tries to do is it tries to combine the subjects with the like features. So here, this looks like it kind of separated the mammals with the reptilians. But it could be something, and again, in unsupervised, we don't know what these clusters mean. So it's just trying to put together similar groups of subjects. So I wanted to know, I was curious to see if we did this with our 7 PCs, how well, or what would the clusters that we can get out of it, does it actually look like the tumor clusters? That was kind of the question that I was curious about. Okay, so I used, there's different types of clustering methods. You might have k-means, there's cluster trees. Those are more of heuristic, I'm saying that word right, heuristic methods, where you're not really estimating a specific parameter. It's not model-based. So this is a model-based clustering technique. And what's happening is here you have a population that has different groups or clusters. And again, you may not know, you probably don't know how many clusters there are. And their popularity, in statistical terms, is known as their weight, is denoted by this pi parameter. So J, number of clusters, and X is your input, and then your parameters that you want to estimate are pi, mean, mu, and then some covariance structures. And typically it is Gaussian that they assume for the form of the density. So a Bayesian non-parametric approach to this type of model would be to place what's known as a Dirichlet process prior on the distribution of the mean and covariance matrix, and then let the model and the data speak for decide how many and where those clusters are. Another approach is the one that I'm going to show you, which is just expectation maximization algorithm. And what they assume a different number of clusters at each point. So they say, okay, cluster, let's say the cluster's 2. Then what would the best estimates for these parameters be? Let's now assume there's 3 clusters. What would the best estimates be? And this is done very quickly, actually, in mclust function in R. And again, I'm just going to input my first 7 PCs. And then how you decide which one is the best number of clusters, there's different methods. So this one automatically spits out to you the Bayesian information criteria. And this you could think of, and it has the word Bayesian in it, so you could think of it as if we had prior knowledge, uniform prior knowledge, so we could think of any any possible number of clusters had equal probability of being the best model. And then we observed our data. Well, the BIC is actually the posterior probability of having a model with cluster blah, blah, blah. And so here's what it looks like. There's several different lines, and those different lines just correspond to different sigma structures. So you can assume a different structure for your covariance matrix of the clusters. And actually we're getting pretty close. It turned out, though, that having 6 clusters was the best according to MCLUST. So higher BC means is better, a better model. So I said, okay, well, 6 clusters, that's pretty close to 5 clusters. Let's look and see it at the plot, see exactly how close we got. So hold on, let me go back to that in a second. So how close we got. So this is the clusters that it tried to make, or that it ended up deciphering for us. Here is the truth. So really close. It seems where the model had a hard time. And this is really telling of this data set. A lot of times these things don't come out this nice because, the gene expression could also be telling us about maybe more than just the tumor types. Maybe there's other features of these subjects that could be classified as well. So it was actually very interesting to see that there is definitely some powerful information in this data set in regards to these tumors. So where it kind of had some issues with is right in here, the kind of these 3. And the points that are kind of blown up a little bit, those are the ones that they're less certain about which cluster they belong to. But definitely these ones we did pretty good. If we went to 5, I'm wishing I kind of showed you the plot for 5. If we went with 5, I'd be really curious to see if we got pretty spot on. But this is already pretty close, so I was impressed with this. So this is, I'll go back now to this lovely picture. So this is, remember we put in our 7 PCs, and this really kind of demonstrates what we mean by information. Oh, sorry.
Just had a quick question kind of going back.
Oh, yeah.
So essentially what you're doing at the beginning, you're using that Bayesian information criterion to determine, or I guess estimate, the appropriate amount of clusters using those 7 principal components that you identified. But that in itself, that depends on what you define to be the appropriate amount of principal components.
Correct.
By that
Correct.
Okay.
Mm-hmm. Yeah, no, that's a really, really good point. So, and these are those things where it's kind of, you should actually explore other types of, or a number of PCs. Like, did it matter if we did 7? What if we did 6? What if we did 8? Like, would we be able to get the clusters to be more at 5 if we went more? Like, exactly. That's a very good question. And I do have a reason for 7 PCs. I promise you it's coming up. So trust me for a minute. Never believe anyone who says, trust me. So, but this actually kind of along your same comment though, this kind of displays the clustering under the MCLUST when you're looking at a biplot of your PCs. So we could see these clusters, and again, there's 6 in here. That was the optimum number that the MCLUST chose. And we really have these defined clusters for PC 1, 2, 3, and then you notice that as we go, these clusters start becoming a little more convoluted. So even here, 7 is probably looking at this like if you try 8, you're probably going to end up with the same, because once you get down to this point, you're not finding features that are like global. It's usually going to be very like only a few data points are going to have that particular structure. So where the story really is up here. So just looking at how well defined these clusters are, really up through PC 1 through 3, we're doing great. 4, these are kind of almost negligible at that point, as far as this MCLUST was pulling information mostly from the first 4. So now we want to kind of go on. We explored, we've got our PCs. And then we kind of investigated with M+. We're very, very certain that these genes are going to tell us something about being able to classify these tumor types. So before I get into it, just a little bit of background on what exactly supervised modeling is. So you have your response, and it's going to be some function of your data, and then plus some error. And this really is at the heart of every supervised statistical model. And you may even see this called functional analysis. Sometimes I've heard that term in machine learning, especially when they're working with Gaussian processes. There's some models that also utilize Gaussian processes. But they call it functional analysis, but this is a very general thing, very general. And depending on what approach you want to take, so if you know something or you have a hunch of what F might be, what structure you should put on your function to get your output Y, you can use some sort of parametric modeling. If you don't, and this is where Gaussian processes tend to be utilized quite a bit in the non-parametric modeling aspect, where perhaps you don't know what that function looks like, but you want to learn what that function looks like from your data. So regression versus classification. So what you want to do is to be able to make good predictions. And to make sure that you're making good predictions, you want to see if what your predicted value is close to your observed value. So, and this is known as, and when you take that difference, square it, sum it, that's your MSE, your mean square error. It's exactly what it says it is. It's the average of your errors squared from the model. And you're probably more familiar with this. But in classification, all this means is you're going to count how many times you misclassified a particular subject. So this is the realm that we are going to be working in with this data set, but it can also be applied in the regression setting. So now, of course, if you utilize your data set to fit your model, then usually and then you go and you predict that same data, you're gonna do better than probably what you would do if you were to try to predict new data. So it's kind of giving you this false sense of fit if you don't divide somehow your data set into a training data set where you fit your model, and then you try to predict using your new data. It's a much more appropriate way to go about testing how well you're doing on prediction for your model. And this really is a straight from machine learning concept, where you divide your data into your test and your training. Now, we know, especially as statisticians or aspiring statisticians, that sometimes just by random nature, you can get different, maybe an outlier in your training, maybe an outlier in your test. So you can get extreme values in one of these sets. So maybe just doing one model on your training and then predicting your test maybe isn't the best way to do it. So then you're getting into the realm of what they call cross-validation, where they say, okay, well, instead of doing it just once, let's do it a bunch of times. So this is the kind of extreme where you just leave one data point out. You fit, because you want a lot of data, a decent amount to fit your model, and then that one data point you will predict, and then you do it again. So now you put that other one back in, and you take the second one out, and then you fit the model on your training, and you try to predict the test, and then you're going to look at you're going to average all of these errors, and then for that particular model, and that will give you a better MSE. So this can be computationally expensive, and there's some theoretical aspects that are also not in complete favor of this. So from a practical and theoretical view, a good middle ground for this is to do something where it like tenfold, where you, instead of dividing just leaving one out or dividing it to just two, you can divide your data into, say, 10 groups. And then you leave one group out for your test, use the other 9 to fit your model. Compute your MSE, tuck it away, and then you go on to the next one. And then, again, now you're taking out fold number 2, and everybody else is used as your training, and then you predict, and so on and so forth, and you can average what those MSEs actually were. So this is how I chose I almost said the correct number, an appropriate number of principal components. Is I went ahead and I said, okay, I went up to about, I think 50 principal components. If I needed to go more, I could, but I said, okay, if I just use 2 principal components, and I did this 10-fold cross-validation, now incorporating my response. So this is the model that I assumed. So we've got a multinomial model. So the thetas represent the probability of a subject being in a particular group. So J is our group. We've got 5 tumor types, and then theta is our probability of being in that particular group. And typically what we do in multinomial regression modeling is we look at the log odds of being in group little j over group big J. So one group acts as your baseline group. So it's your, and then you set a linear regression. So what I did, so P here has this question mark because that's what we're trying to find. How many features or attributes or inputs, how many other names can you come up with with the values that we put into our model to try to predict? All of those things are used interchangeably, just in different fields and have a preference for the verbiage. But how many do we need? And so what I did is I just fit this model over several different possible number of PCs. And then I looked at my prediction error. So I did this non-Bayesianly, but I am a Bayesian, so I couldn't help myself but put this in here. If you wanted to use the Bayesian paradigm, then you can just place, typically they'll use normal priors on your the effects of your coefficients. And there's a package, I think it's mlogit, the paper associated that will do this automatically. Okay, so how many PCs do we need? So I did cross-validation to the rescue, and here we go. And I will say the error in general was quite small. So this was the number of misclassified subjects, and I just did it, so the point estimate, the red is just the quantile. I didn't want to take average because we're dealing with counts, so that's why I went with quantile. And then a 95 kind of interval estimate for the misclassification. And there was about, so in 10 folds, there was about 100 subjects that we were predicting each time. So our misclassification rate, kind of on average, if you will, was only about 3%, even with just 2 principal components. But we want, this is where I'm assuming we want as low of misclassification as possible, especially dealing with some diagnosis of some, I'm imagining in my mind, if we misclassify and give a wrong treatment to a person, then that's absolutely detrimental. And again, it's not my field, but in my mind, that was my motivation for getting as low as possible. So pretty much after 7, we're not getting any more reduction in the misclassification. And in fact, many of the folds, we got perfect prediction. There's actually 0. So that is why I was on 7. Yes.
Kind of follow up then. So I guess what this is saying is that by classifying something properly with that cross-validation, you in a sense say that the additional physical component is not quote unquote interesting, I guess. And so therefore, it doesn't really contribute any additional information. You
Correct.
Stop that there.
Yeah, correct. It's not helping us to get better prediction. Okay, so at the end of the day, so I went with 7. Oh, sorry, excuse me.
Well, I'm just wondering why the uncertainty fluctuates a lot, especially if you add more PCs.
I know, right? So it almost seems like there's, and I think that's the importance of the cross-fold or the K-folds cross-validation, because it just really depends on the mix of things. So some folds, we happen to get more extreme values in one side or the other, so it may cause higher or lower misclassification. So probably what's happening here is perhaps there's like some sort of overfit going on, so that we've got too much, the model's too trained to some of the training data, so that this prediction now becomes not as accurate for new data.
So presumably that would change if you use, say, a 12-fold or a 20-fold or whatever. You use that 10.
So Valerie, so from the health science research perspective, this is almost like putting variables into a model, right? And if you put more and more, you over adjust.
Correct.
And
Yeah,
so
exactly.
you want to try to figure out what are the, like, you know, if we're looking at cancer as an outcome, what are the factors that are going to predict it the best without over adjusting your model, right?
That's exactly, yeah, that's exactly correct. So with 7 PCs, this is the model fit. I highlighted the coefficients that were particularly high, because then I'm going to look at those PCs, and then I'm going to say, okay, well, which genes in those PCs had particularly high weight? And then kind of, and this is a kind of an ad hoc way. Now you can, remember these PCs are a function of all the genes. So you can put that back in and you can get a model as a function of your original genes. And then just pull out what the highest weight is. But you gotta remember the interpretation of these coefficients. So this is the log odds of being in co-odd versus BRCA. So it's not just the contributing to probability of co-odd, it's the log odds of being in the co-odd. But this still will kind of wrap up the story kind of nicely, where while you can do a little bit further, more formal analysis to really pull out the appropriate genes, but a good way to kind of just get a practical sense of which genes are important. I'm just going to look at which genes had the highest weight in these in the PCs. And I also pulled out PC2 because from before, so it has like a decent weight across all of them. So while it may not, PC2 may not distinguish from BRCA exactly, it probably is still important. So that's what I mean by watching the coefficients, what they really mean. This is really just how well we can distinguish each of these groups from the BRCA group. Okay. So these were the top 2 weighted or contributors for each PC, each principal component now, or component. And so I just went ahead and we're just going to look at biplots of each of these, the first 2 top genes in each of the principal components. And so you can kind of see which groups get pulled out. So the first principal, those first 2 genes really pull out the Kirk group. They distinguish Kirk from everybody else. And this guy, PC2, really clear cut on its own, is able to distinguish the prod. And then PC3, which seemed to be a pretty good player, also can distinguish prod, but and then on top of that, it kind of pulls out that BRCA. And that's why PC3, when you go back to the model, PC3 had a pretty high weight, so it appears here, here, and here, because again, we're relating it to BRCA. That's why it pops up so much. And then finally PC, this is PC6, I believe is what I pulled out. Yeah, PC6. Really seems to pull out Luan. And you can do this as well for the other pairs and kind of get an idea, or do it a little more formally by inputting back the PCs as a function of the genes. Okay, so then we say to our friend, I've got the best model in the world. Send me some new people. I gotta prove to you that this is the best model in the world. Everyone's gonna get the right diagnosis. So they send you 10 more people, and you put it in your model, and this was the result. So this is what the model predicts, and this is our actual. So we only had Burka, Kirk, and Prod in our 10 samples, but we had perfect prediction. Burka with Burka, Kirk with Kirk, Prod with Prod. So we get a perfect score. Again, this is not always, this is a good data example. When I found this data set, I was actually really just like in shock and awe of how well these things turned out. I will warn you, that's not the case. I mean, it's like, instructors always show you the easy examples. But this is real data, and so this is a real life situation. But these are the things that the machine learning or statistical learning tools can do to answer these real world questions. So, Sam the man, about to take on over for the rest.
All right, yeah, it's just a quick question.
Oh, yeah.
We're just going back a slide. Hey, what if your friend sent you something that was a 6 cancer type?
A 6 cancer type.
Yeah, just to like do your curveball, would it, like, would you predict that it would fit in with one of these 5?
You would force, it would be forced to.
Go into one?
Yeah, you would be
It would
forced.
be trained as an outlier.
Now, so I mean, it would be interesting to see what exactly it does do with it. But yeah, it would have to, because your model is 5 tumor types, so you'd have to use a different model. You know, I'm actually already kind of thinking like of models that we could use to try to make it. And I'm thinking Bayesian non-parametric is that you've got the option of having a second group.
But if you give me another tumor type, I do Bayesian analysis because I've already accumulated knowledge on 5 tumor types. And the way I do it is, what Valerie is showing you is called feature extraction in statistics. And feature extraction was exactly identification or solidification of those points on the corner, basically through different PCs. So geometrically, principal component analysis is a mapping or a translation of the geometry of the original space that had 20,000 dimensions onto a smaller space that has 7 dimensions, let's say. What you're talking about is adding one more axis to the geometry of the axes of the principal component. Suddenly you find yourself in the realm of an 8-dimensional geometry. Therefore, there is a one-to-one mapping from 7 dimensions onto this 8. Mathematically, there is such a thing. The connection between 7 dimensions onto the 8th dimension. That updating is done through Bayes' theorem that I showed you in the beginning of the story. You know, essentially, not throwing away everything that you've already gained, but to utilize what you already know in order to predict a new dimension. Obviously, the variation or confidence interval of your prediction is going to be very high, because by adding a dimension, you're adding a dimension of 20,000 features to the story. So you have to talk with a lot of variation, uncertainty. Nonetheless, it can be done mathematically. It's just yet another projection from the existing space onto a new space. People do that all the time, actually. Cool. It's very, very cool. Yeah, it's the magic of feature extraction. Okay, so I know everybody's tired and you heard a lot of these things. So I was curious. I said I talked about neural networks. Valerie's doing cool stuff. I have to do some cool stuff too. So I got my neural nets trained for her gene expression data. Let me just say that, you know, the idea, just to remind you that input comes in, data comes in. Data here is big. Somebody, I think NAL asked what constitutes big data. Data here is big. Think about it. She has 800 genes. Each gene has 20,000 dimensions. 20,000 by 800 is, I don't know, some big number, isn't it? That's big data. Many, many years ago, they couldn't even imagine doing this type of analysis. 30 years ago, it would cost you months of computer processing. 10 years ago, your usual PC would have collapsed. So you needed when I was at Carnegie Mellon, we had to do these types of things with parallel processing, right? But nowadays, she runs this with her laptop. That's cool. So that shows you the trajectory of computational facilities or hardware and how it contributed to our perception. And now they're talking about terabytes and petabytes. That's 10 to the 15 or something. Who's the? Do we have a computer scientist who can translate petabytes? That's considered big data. I don't know what that is. It's 1 1 and many zeros. But this is big data. Okay, so I'm doing two types. When I write an elaborate neural network like this, mathematically, I'm doing two types of transformations. I'm getting my red input observations, I'm putting them via those weights betas onto an activation function called F. I'm creating that hidden layer, which is blue, and I'm subjecting that blue set of perceptrons onto yet another transformation, which is called G, and I'm outputting stuff into different categories in green. How do you choose those activation functions? There's a whole host of possible scenarios. You want your activation functions to be nonlinear, at least for the hidden layers in between, and potentially binary for the output layers if the task is classification. Nonlinearity actually allows for better mixing of the layers of your neural networks. Why should neural networks work? How do I know this classification is done? If you take our graduate course, we actually mathematically prove to you that there is a convergence that happens as a limit theorem that will allow you to show that you will reach to a solution, potentially a good solution, in finitely many number of cycles. Okay, that's the very famous perceptron convergence theorem. It works mathematically, so it should work in real life. How does it work? It works through an algorithm which is very clever. It's called backpropagation algorithm. It's basically a feed-forward technique. At every single time, for those of you again who are more inclined mathematically have seen these stuff, it's a sort of an algorithm called gradient descent algorithm. Basically, it looks for optimal points in a greedy way. It finds it and just optimizes it and moves forward. It's a really, really cool story. All you need to know is basically Hessians and differentiation, calculus one. So with that, you can run this show. How many layers? Somebody asked. I can extract more features. I can add to the accuracy of the scenario by adding more layers. But I can do what Valerie does, which is cross-validation to decide what number of layers. I should have in mind that every time you do mathematics or statistics, I prefer smaller models. Models that are economically smaller and are telling the same story. That's actually a philosophical point. It's called Occam's razor. Basically, if I can tell a story, what we call a statistical inference, with a very elaborate, highly structured model, that's option one, and a tiny little model that no one else does the same thing, I prefer model 2 because it's more interpretable. I can tell a story to the non-statistician, to the scientist in more meaningful ways. So I applied cross-validation. That's Valerie's data to her PCs, and that's her. That's the tumors in her data set. And I can do all the classic cool stuff that she does with my neural There's sort of a rivalry thing going on here. So I look at my PC1 and PC2 with neural networks. This converged in a fraction of seconds. That's super awesome. If I wanted to add more elaboration to my network and make it more complex, I could have done that. And so, once I got it, it was like 2 a.m. I emailed her and said, I have it. Just to let you guys know, statistics, mathematics, computer science, they're all moving towards computation and application. If you look at the trajectory of statistics, it starts from upper left corner and sort of does a little turn and comes back up. One angle is applications, the other one is math, the other one is computation. When statistics as a discipline started in 1900 by Carl Pearson, it was merely an application type of story. He wrote a paper on chi-squares exactly in 1900. He came up with a journal called Biometrica. He published it. There was no such a person as a statistician. Everybody was either a mathematician or scientist. And then he analyzed data from what the correspondents of the British Empire were sending out to their headquarters in terms of observing people's characteristics from different corners of the world. He published them in Biometrica and he calculated correlations, basically. That's how modern statistics starts, exactly in the year of 1900 in the Journal of Biometrica. In 1908, Gossett wrote his famous paper, T student, he called himself T student, he was a shy guy. He wrote a very sort of elaborate paper, which is called, which sort of coined the term of T statistic. 1925 is the year that R.A. Fisher came up with maximum likelihood estimation. Estimation paper of Fisher is very, very famous. He sort of dabbled on the idea of hypothesis test and so forth. 33 is when Neiman and Pearson wrote their famous hypothesis test paper. Became very mathematical. 1935, Neiman published a paper on confidence intervals. It's a very, very hard paper to read because it's very, very mathematical. 1950, Abraham Waldman wrote a famous paper, a book actually, a thesis, which is the modern treatise of decision theory, what we call decision theory. 62, John Tukey started talking about data analysis. He called it exploratory data analysis. From the 70s on, 79 is Efron's bootstrap. It now becomes more and more applied. It became very, very mathematical. Statistics department in the 50s were all math, proving this and proving that. But in the 60s and 70s, they moved towards applications and computation. By the year of 1995, the idea of machine learning comes to the fore, if you will. And you actually see people talking about classification and those types of things. And then there are really two types of statistics. In 2016, when Efron and Hastie published this sort of review, where 2016A is one direction, which is more of the machine learning side of statistics. 2016B is more of the statistical data analysis. But it's really now the combination comes to the middle of this sort of triangle. Modern science is math, is statistics, and it's computation. What we showed you here comes with a lot of technical stuff. We skipped them because they're easy to learn, right? It's the concepts that do matter. Everybody can learn those math stuff. This is really hot stuff, okay? If I were a student, and if I do it again, if I were in your shoes, for the students in the room, I would somehow get involved with this stuff, data science, machine learning and stuff. Students coming back to me and telling me that, when they know these things, when they claim they know these things, they can land on really fancy jobs. We have good master's programs in statistics, applied math, along with many awesome master's programs in this college. And we have statisticians all across the department who are willing to talk to you. If you have data problems, you don't have to reinvent the wheels. Just stop by. As long as you buy us coffee, we're willing to help you. There are all sorts of opportunities. We have a big grant on big data. It's an NIH grant. It is supposed to bring the culture of big data analysis to this campus. It's a $1.3 million grant. And we have a center which is hosting this event today. It's called the Center for Computation and Applied Math. And basically, we're willing to help you. If you're more interested, we do more of these workshops and stuff like that. And we really thank you for your time. And we know that it's a Friday, coming in here, deeply appreciate it. Thank you very much. Before we close, number one, there is refreshments outside the room. Number 2, there is a grant writing workshop that's CCAM is co-sponsoring. Michael, do you want to say something about it? Where is it going to be? What time?
This is for Grand Happy Hour.
Yes, please.
Yeah, so we also, through CCAM, we run this thing called Grand Happy Hour. This is for faculty, probably mostly, but anybody who's interested in writing grants, it's basically a support group within CCAM to work together. We have people from the Office of Grants and Scholarships that come down. They work with us as well, so you can talk about anything. Every so often we have, they do a presentation on basically some aspect of putting together a grant. So you're more than welcome to show up. It starts, we're going to do one again today at 4 o'clock. It's in MH 531.
I would go. Thank you so much.
I look
And
forward to seeing you there.
yeah. And Ren, can you say something about your work?
Yeah, even this evening today at 5 at MH 380, we have a panel of statisticians who are going to help our undergrads today, specifically for next weekend's Data Fest competition. That is a competition that is solely about big data. So what's going to happen is it's going to be a Q&A session, possibly a little breakout to have some interactions, possibly get to know a little more of the software.
Where is it going to be again?
It's going to be at 380.
This building.
This building, 380, and that's going to be at 5. So if you're interested in sitting in and hearing these types of introductory questions, some big do's, some big dumps, maybe just in your ideas of how you would like to start with big data or further exploration in which you would like to do professionally, the Data Visualization Club, hashtag DVC rules, thank you. That's going to be tonight, hosted by the Data Visualization Club.
All right. Thanks again, everyone, for coming.